Hello, welcome to our little corner on the web, where we hope to instill and develop a love for math. Today, we will go over questions 7 through 9 in part 1 of the 25th Philippine Math Olympiad. So, flashing the questions here now for those of you who want to give it a try first before you look at the solutions that we have for them. First question is from, I guess, algebra, functions and logarithms. Second question is about the geometry. And the third question is a mix of number theory and counting. Okay. So feel free to pause here and give the questions a try before going further. Okay, diving into question 7. Question 7 asks, let k greater than 1, the graphs of the functions f of x equals the log of the quantity square root of the quantity x squared plus k cubed, close quantity, plus x, and g of x equals 2 times the log of the square root of the quantity x squared plus k cubed, close quantity, minus x, have a unique point of intersection AB, find 2a. So having a unique point of intersection means that there's a unique solution that satisfies both. So there is a point where f of x equals g of x, and that point is at x equals a. So we can start writing the identities that we know, or the equations that we know. So we know that for some a, f of a is equal to g of a. So that means that log of the square root of a squared plus k cubed plus x is equals to twice the log, oops, sorry, not plus x, plus a is equals to twice the log of a squared plus k cubed minus a. Okay, rewriting a bit, the logarithmic identities, log of square root of a squared plus k cubed plus a is equal to log of the square. Okay, a squared plus k cubed minus a squared. Okay, since the logs are equal, that means that the arguments must be equal. Okay, so simply we can write it as a squared plus k cubed plus a is equals to a squared plus k cubed quantity minus a squared. Okay, the first time I actually got to this point, I expanded the right side, tried to play around with it. Couldn't get anywhere meaningful. So I had to go back to this exact line and ask the question, how do I get rid of those radicals somehow? I got an inspiration from looking at the left-hand side being basically some x plus y, and the right side being some form of x minus y, to say maybe I can use one of them and have a difference of squares. So I basically did a multiply on both sides of the square root of a squared plus k cubed minus a. Okay. To see what happens, let's just go ahead and try it. The left-hand side becomes a squared plus k cubed minus a squared, the difference of squares. Okay. And the right-hand side becomes a cube. A squared plus k cubed minus a quantity cubed. So on the left-hand side, a nifty thing happened. The a squares cancel each other. So now we have a perfect cube equals to a perfect cube. So we can take the cube root of both sides. So we have k cubed equals, oops, sorry, k, taking the cube root. We have k equals the square root of a squared plus k cubed minus a. So transposing, we have k plus a equals a squared plus k cubed. And then now we can actually square both sides and get rid of that last radical. Okay, so let's see if we can fit the rest of the solutions here. So now we have k squared plus 2ak plus a squared equals a squared plus k cubed. Again, the a squared cancels. So we are left with 2ak equals k cubed minus k squared, or 2a, which we are looking for, equals k squared minus k. So the final answer is D, k squared minus k. Okay. Moving on to the next question here. Okay, question 8 asks, the sides of a convex quadrilateral have lengths 12 cm, 12 cm, 16 cm, and 16 cm. And they are arranged so that there are no pairs of parallel sides. If one of the diagonals is 20 cm long, and the length of the other diagonal is a rational number, what is the length of the other diagonal? So there's only one arrangement that makes sense here for the 12, 12, 16, 16. The 12s must be beside each other, the 16 beside each other, because if not, if they're opposite, then we have a parallelogram. So we can draw this now as 12, 12, 16, 16. Since we're given that that one of the diagonals is 20, it's actually very tempting, and actually it is the correct one, which is to put it right here. So we have a 3, 4, 5 triangle, a 12, 16, 20 triangle. So since it's 12, 16, 20, we know that that's a right triangle. So we can calculate the area of the kite as no more than 12 times 16 over 2 times 2, meaning the area of the right-hand side and the left-hand side of that kite. Okay, so this is simply 192, which is the area, again, of the kite. Another way to find the area of the kite is through the diagonals. So D1, diagonal 1, times diagonal 2 over 2 is another way to express the area, which we know is 192. So therefore, 20 D2 over 2, which is 10 D2, is equal to 192, or D2 is 96 over 5, okay, or C. Okay. You can actually try, just for investigative purposes, putting the diagonal 20 this way, and you will find that you will get an irrational diagonal on the other side. Okay. Okay, moving on to the next question. Question 9. How many numbers from 1 to 10 to the 4th can be expressed as both the sum of 5 consecutive positive integers and as the sum of 7 consecutive positive integers, but not as the sum of 3 consecutive positive integers? Okay, first let's figure out what it means, or how we can represent the sum of 5 consecutive positive integers. Okay, one way to represent this is x minus 2, x minus 1, x plus 1, x plus 2. Okay, in this way, if we sum them up, we actually get 5x. Okay, and since we want x to be positive, we know that x here should be, or all the integers to be positive. We know that x here is greater than 3. Okay, it really won't matter later, but it's just something to note. For 7 consecutive positive integers, then we can write it as x minus 3, x minus 2, x minus 1, x plus 1, x plus 2, and x plus 3. So if we sum them, we simply get 7 over x. So if we want the the numbers that can be expressed as both the sum of 5 consecutive positive integer and the sum of 7 consecutive positive integer, then they must be a multiple of 35 y, right? It's a multiple of 35, meaning it has to be the multiple of the LCM of these two. So really, we're looking for multiples of 35. Okay, so 35y. That's what we're looking for. Okay, but we want that it's not the sum of 3 consecutive positive integers. So 3 consecutive positive integers we can write as, x minus 1, x, and x plus 1. So that's 3x. So we don't want them to be a multiple of 3. So the only multiples of 3 that's also a multiple of 35 is actually 105z. So some multiple of 105. So we don't want it to be a multiple of 105. So we can just actually find out how many multiples of 35 there are between 1 and 10 to the 4th and count the number of multiples of 105s that are there and subtract them. Okay? So we just take 10,000 and divide it by 35 to get the number of multiples of 35. So that's 278, 280, 105. So there's 285 multiples of 35. It just so happens that 285 is a multiple of 3. So we actually have an easier life here. We just multiply 285 by 2/3. And we don't have to make any more adjustments because every third multiple of 35 is 105. So it's really just deleting every third multiple. And since there's nicely 285 multiples of 35, we don't have to make any adjustments on leftovers and whatnot. So this is 190. So the answer is B, 190. Hopefully these solutions are helpful and educational. If you found them to be so, do press the like button and subscribe. Thank you for watching.